Okay, so today we're going to continue on with the multi-phase flow equations that are typically solved. And so what we discussed last time was the derivation, or not the derivation of the formal multi-phase flow equations, and those are what's called an Eulerian approach, where you use an Eulerian method for the fluid and an Eulerian method for the particles or liquid or basically what have you. And again, there are pros and cons to the Eulerian approach. And then the other alternative for multi-phase flows, if you have either a bunch of droplets or a bunch of solid particles, is what's called an Eulerian Lagrangian approach, where you basically treat the particles or packets of particles as Lagrangian elements, and you use a sort of bunch of techniques with that. And Baer's group are one of the is a world-renowned expert at doing that stuff. But as accurate as those are, those do have some limitations. Just remember, for combustion, the particles are very, very small, on the order of 1s to 10s of micrometers. And so if you count up the number of Lagrangian particles that you would in principle have to track, it could easily be in the trillions. And so that is not practical for basically anything. And there's another subtle issue with those methods, and I'll get into that after we sort of discuss. Because there's kind of in combustion, there's kind of a myth going around that Lagrangian methods for particles are always more accurate than an Eulerian method, but that's not true. There are some really subtle things that you need to worry about. But if you have the type of flow where a Lagrangian method is superior, it is by far superior. There is no comparison, and I will discuss those pros and cons later on. But right now we're talking about an Eulerian two-fluid model, and the sort of or five equation model or two-fluid model. They all go by the same name, or they all go by different names. And so we derive this by assuming homogeneous flow, meaning that the velocity of the gas and the liquid are the same, and that they're in mechanical equilibrium, meaning that the pressure of the gas and the liquid are the same, and that they're in thermal equilibrium, meaning that the temperature of the gas and liquid are the same. And then what you do then is you can combine the sort of formal, you can combine conservation of momentum and energy for the gas and particles into one sort of master equation for the mixture momentum and the mixture energy. And this greatly simplifies the solution process, because these so-called nozzling terms, the P grad alpha terms, those terms are absolutely awful to basically try to include. And then if you're not careful, those terms, if you were to do a formal, you do this in gas dynamics, but not here. If you were to compute the sound speed of your governing equations, these evil sort of nozzling terms here can make the sort of sound speed for the gas particle mixture complex value, which is of course unphysical. And so dealing with these, so basically these nozzling terms look innocuous because they're just pressure times a gradient, but they cause all sorts of mathematical problems, which we're just learning how to deal with. And so, but anyway, so we got the 5 equation model here, and then if you add species mass equations, and if you carefully account for heterogeneous phase change reactions, those could be, if it's some liquid propellant that's pyrolyzing, it could be a sort of pyrolysis law, or it could be a vaporization law if it's a boiling droplet or just a vaporizing water droplet. And then you have also gas phase chemical reactions. Okay, and then note, we sort of noted this last time, but for each phase we do need an equation of state, because for this model, each phase is modeled as a compressible material. So that is the liquid. You need a formal equation of state for that. And those go by, and there are several of those that are simplified. There's a so-called stiffened gas equation of state. I think I wrote that down in the slides way back. There's also Tate equations of state, and there's other things that are used for, say, compressible liquids. And for solids, you can also use the same approach for solids. Braden is working on that. And those sort of equations of state for the solid get very, very complex because they also depend on the strains, which is a whole nother can of worms. And I'm not going to get into that here. And then basically after you've chosen your equation of state for each phase, then you can basically solve it and sort of just let them go. And then just note that you need to find pressure and temperature from the conserved variables here. And so in general, there's a sort of Newton-Raphson solve that you need to do that. Professor Stewart does have some sort of simplified procedures that, at least for explosives, where your two equations of state are a solid equation of state for the unburned explosive, and some sort of product equation of state at Chapman-Jagay like detonation conditions. He has a sort of nice simplified way of sort of solving this. That's just a linear mixing rule based on empirical evidence from their numerical experiments. But in general, that rule may or may not hold for if you have a gas liquid surface where there's a density jump of over 1,000 kilograms per cubic meter at the gas liquid interface. I don't know if that mixing rule sort of works well or not. And so I am just listing the very general way of doing this. And note that if the code breaks, if you implement this model into a code and the code breaks, it is almost always at this step right here. Because one of the most difficult things that you can do in all of modeling and numerical methods is find roots. As you guys are finding out with both project 1 and project 2, is that those are essentially massive root finding problems that you are solving. And so basically root finding is one of the most complicated things that you can do, especially for some of these equations, just due to various thermodynamic inconsistencies. If you're dealing with, say, JWL for the products, it is not unheard of for there to be sort of singular poles and things like that when you're trying to solve these equations here. And so you sometimes need to guide the solver away from those things. But the details of doing that are so specific that I'm just going to let you know that things like that exist and you need to worry about them. Okay. And now, so we use, there are multiple ways of solving these methods or solving these sort of equations. One is the volume of fluid method, where basically you use this really complex geometric reconstruction algorithm of the interface. And the nice thing about to basically keep the interface very sharp, and these are traditionally used in spray atomization. So I'll show a movie of that. So let's see, what's the one I want? So this is a movie of from Olivier Desjardins. He's a pretty famous, for low speed flows, he's a famous multi-phase atomization guy. And so at Cornell. And so this is a simulation of a diesel-like jet being injected at diesel-like conditions. This is a direct numerical simulation, meaning there's no subgrid modeling, there's no turbulence modeling. They are solving the they are solving the volume of fluid equations for a gas liquid flow. The only difference between the ones that I presented and the ones that they are solving is that they are assuming incompressible flow. And so there is they have an incompressibility constraint instead of an equation of state. And so that version of there is also a low Mach number version of the VOF equation, but since we're working with propellants and explosives, everything is compressible. But I will show you this movie here just to give you an idea of sort of the power of these VOF methods if you can get them working. So yeah, this was a really big calculation back in the day, about 10 years ago. 1.6, basically 1.3 billion, basically billion grid points, and they solved it on a really high performance computer, at least at that time, on 12,000 cores. And so this is a VOF method. You see all the droplets being stripped off, sort of things like that. And so those are inherently being captured as just part of the VOF algorithm. They're not assuming any breakup model. As the liquid jet becomes unstable, again, as the liquid jet becomes unstable, the surface instabilities on the surface of the jet are just part of the solution process. So these VOF methods are really good for understanding really highly dynamic evolving surfaces. And because it is a mass conservative method, you can be assured that all these little droplets that are being stripped off to the side are conserving mass, and they won't just disappear. If you were to do the same the same model using a level set method, you would wind up losing those small droplets would just disappear due to numerical dissipation. So are there any questions on this?
You said something about there's no turbulence model within that because it's a direct numerical simulation. Can you?
Yep.
So then I guess I'm trying to understand exactly what that means. Like that solving the VOF method directly, does that mean that it computes turbulence in that equation?
Yes, fundamentally turbulence is part of the Navier-Stokes equations themselves.
Right.
So if you highly resolve your flow, you do not need a turbulence model, and that's called a direct numerical simulation.
Okay.
Yeah. Okay. If you resolve everything, and so here they may not be resolving all of the turbulence. I think I might have mentioned this in passing before, but the direct numerical simulations actually means different things to different groups. But almost always, but the sort of turbulence folks, to them, it means that you are resolving all scales of the fluid flow down to the Kolmogorov scale of turbulence, which is the smallest scale of turbulence before all your little sort of micro eddies basically dissipate into, due to viscous dissipation. But also in multi-phase flows, direct numerical simulations also mean that you are not using any subgrid modeling of the evolution of the interfaces. And so if the droplets strip off, they strip off. You have no model that is describing that process. And in those, the sort of multi-phase community will call those direct numerical simulations, even if they aren't fully resolving the turbulence. So here, I don't know if they're doing a DNS in the sense of turbulence, but in terms of particles, they are. And they are certainly at very fine length scales, because those droplets being stripped off are really small. So in all likelihood, if they're not a actual turbulent DNS, they are really darn close to that. Okay, so just be sort of careful with that. And also, if just a word of advice as someone who made this mistake, the turbulence folks basically planted the flag that they lay claim to the phrase direct numerical simulation. So if you go to a conference and you say you're doing a direct numerical simulation, even in your field, if it's a direct numerical simulation, the turbulence people will always raise their hand and ask you, are you fully resolving down to the turbulence? And if not, in their eyes, we're not doing a DNS. So just be aware of that. I know like in some fields, they're very careful with this, like in Bala's group, because he's mainly a turbulence guy with particles. So he gets around this by when he fully resolves his particles, he calls those particle resolved direct numerical simulations, just to add a thing to that, possibly in part to avoid this thing, and also to be very descriptive as to what he's actually doing. Okay, so are there any other questions with this? And these VOF methods, they're used for all kinds of things. They are used to study the wakes that form around ships, all sorts of sort of gas liquid flows. These things are used for. Okay, and then I also discussed the so-called sort of think method, which is sort of halfway between a diffuse interface method where you don't use any special treatment of the interface. You just solve them using your normal compressible flow algorithms, and think. And think is sort of like a VOF method, but not quite as complicated. And so this is a simulation I did of a Mach 5 shock wave, and it's going to be interacting with an array of water cylinders. And so this is solving the same 5 equation model. I use a stiffened gas model for both the gas and the liquid. And so we have a Mach 5 shock wave, and we just basically solve the equations and then just let them go. So we have a shock wave going over the droplets. There's an interesting shock droplet interaction, but the key thing here is the model itself is that it's sort of able to get the shock wave and the shock wave droplet interaction and all the wave dynamics that occur inside of the droplets and the droplet stripping and things like that. And so these are really powerful techniques that are opening the door to a lot of fundamental physics. And what we're trying to do is right now these droplets, they're not changing phase, but we're going to add phase change and then allow them to burn up. And so this is a think approach, is that if you were to zoom in on the interface here of the gas liquid, I don't remember what it is for this computation, but it'd be spread over probably about three grid points. So are there any questions with that? Okay, and I'll show some more. This is a diffuse interface method. Let's see, gotta find that.
Do you have experimental data that you can match to these too, to look at suspended droplets and when they get hit with a shock wave?
There are, but the diagnostics, the bulk dynamics of the sort of main droplet is sort of it does fairly good, but there aren't any really good measurements for this kind of shock wave of all those sort of micro misty droplets. They are far too small, and so. But yeah, and so that is something that you're going to run into in this area too, is that a lot of this sort of sciencey stuff that we do in multi-phase combustion is still very much at the applied physics level. And so sometimes you need to do simulations and computations blind. And I like to sort of joke that we like to put theory and experimentation back in their proper order. Because right now the trend is you can only do the simulate. I mean, we have trouble publishing sometimes for this, is because in the modern way of thinking is that you can only do the computation if there is an experiment. And that puts in, I'm getting on my soapbox here, but that's putting theory and experimentation in the incorrect order. And so, and I think part of that is that a lot of that thought comes from engineers in traditional areas, to where the physics is sort of settled, and the simulations are a bit more sort of routine. In this area, there's nothing routine about them. There are arguments over which equations to solve even, and so this is at the applied physics level. And so there are some things you just have to basically put a model together with no experimental data, explain the model results. Hopefully those results will then motivate future experiments. If they match well, great. If they don't, then you actually learn more about the physics because you got to go back to the drawing board and think about where your model went wrong. And then hopefully in say 20, 30 years or however long it takes, these simulations start to become sort of routine. And then we can start to sort of treat it like a more traditional engineering type of simulation capability. Okay, but here we have, this is one of my first calculations I did when I was getting that two fluid method working. And so here, this was a diffuse interface method. And so there's no special treatment, there's no think, anything like that. And so this here would be the volume fraction of the liquid. And so you can see that the volume fraction of the liquid is becoming very smeared out. The interface itself is becoming very smeared out. And so it's not very sharp. It's getting the bulk dynamics right. But all the fine details with like all these small little droplets are all being smeared out just due to how diffuse that that method is. And it's even in the name, diffuse interface method. Now, when I did the same calculation and I switched to this think approach, which forces the interface to be split over no more than like 3 or 4 computational cells, then I get this kind of result here, is that I get a much sharper droplet. I have actual little droplets being sort of being stripped off, and so it's starting to respect the physics a lot better. And I apologize for the quality of that movie. It was just a little test movie of basically when I was getting the algorithm to work. Are there any questions on this?
So in these two plots that you're showing right here, is this again like a shockwave going over them, or is this just like a droplet in fluid flow?
No, this is a shockwave going over them. Again, okay. I can't remember the Mach number.
Yeah.
But it is a shockwave going over them. I just changed the algorithm that is being used to solve them.
Was this kind of like a little preemptive thing you did before the more intense one?
Yep. I always did things like this, and you'll find if you work in the area of developing methods, you'll always do little test things like this to compare things.
Yeah.
And so the first thing I did was I did the diffuse interface method because I didn't have to do anything, and then I implemented this sort of think type of approach, and then got much sharper interfaces and sort of things like this. And so
that kind of.
Go ahead.
So in that kind of drove, did you do the diffuse one first? Obviously it's simpler. And then if you were resolving enough, would have you gone ahead with that? And then you did the think one because you wanted to see if it would resolve the interfaces a little better?
Yes. Okay. Sort of precisely. But also if you have a very strong shockwave interacting with a droplet, you will split the droplet into on the order of 1 billion smaller subdroplets. And so if you were to calculate the resolution you would need to resolve all of those droplets, now granted there is a size distribution of those stripped off droplets, but if you were to basically capture say 90% of them, your grid size would be probably 1 million grid points, on the order of 1 million grid points cubed, in order to capture the droplet dynamics, and the advection of the shockwave, and then its effects. It gets to be a giant calculation, and so basically what that means is that we can't use. In principle, you could use a diffuse interface method and just resolve the bejesus out of everything. But that's not practical, so you need to use these other sort of sharpening techniques to sort of keep the interface sharp. Go ahead.
Yeah, and so obviously the Cornell video is looking at a little bit of different dynamics. It doesn't look like there's a shock wave there, but did they resolve to the lowest length scale, or are they doing any AMR, or is that straight up just a super fine mesh?
On this one here,
Yes.
straight up super fine mesh.
Okay.
And it's also incompressible flow, so that sort of makes things a bit more tame.
Mm-hmm. That makes sense.
Okay, are there any other questions?
So what is that a difficult step for the phase change? Why wasn't that implemented in the beginning? Does that cause a lot of issues, or?
It's sort of, there are some subtle issues with that when you use these approaches, is that you need to this sort of region back here is called micromist. You need to develop a phase change model for that, because basically that is fun. Even this region here is sort of called micromist. It's those really fine little droplets that are being stripped off. So you need a phase change model for this. Where basically subgrid, you are assuming there are a whole lot of very tiny droplets, and then you need another phase change model for when you have an actual interface. And developing that, and that model does not exist. And the ability to sort of connect those two does not exist yet. I know there are calls for proposals on liquid fuel rotating detonation engines, and a lot of the folks that are pursuing that area have not thought about this issue, and they are going to run into it very, very quickly. And that's something that we are working on, or what Skylar was working on, was actually developing that technique. But yeah, and so no, I mean, like when I say these simulations are cutting edge, they are cutting edge. This think approach that allows us to do this, and the other movie that is now behind a window, that's right here. That allows us to do this. Those didn't exist 10 years ago. And so this is very, very cutting edge stuff. Even if it's non-reacting, it's a very, very cutting edge type thing. So yeah, are there any other questions? Okay, so back to the thing. Okay, and so those are the 5 equation models. They can be extended to all sorts of things. And as I said earlier, we are working on extending them towards a reacting flow with phase change. And so in principle, like volume of fluid, you could add combustion and phase change to that. Again, those are huge computations. I haven't followed the low speed. I haven't followed the low Mach number flow world in quite a while. It'd be hard to think of somebody not doing, not allowing that sort of spray atomization simulation to vaporize and burn, but that would be a very large computation. So I don't know how practical that would be these days. It might have to be so it may or may not exist, but I know the volume of fluid method has been used to do like single droplet combustion and sort of things like that. And so eventually there will be a scale up from single droplets to multiple droplets, and then eventually to sprays and other things. Okay, so now there's another if you work in compressible flow and explosives, there's a very famous set of multi-phase equations. They're called the Baer Nunziato equations, or it's called a 7 equation model. And these are often used for explosive detonation, shock to detonation transition, and all sorts of things. So the idea of these equations is that for an explosive, it's not a pristine, and a stick of dynamite is not a pristine, completely solid crystalline material. It's actually a multi-phase mixture that contains some energetic crystallites like HMX crystals, RDX crystals, Petin crystals, etc. Some sort of binder to hold it all together, and then even some small small little pockets or small little bubbles of air that are trapped inside. And so getting those details and understanding, if you want to understand how the explosive detonator, how it can be ignited and transition to a detonation, understanding the interaction of all of those features plays a pretty huge role on basically everything. And so there's the Baer Nunziato model was basically developed for that. And so what they really do is they solve, in principle, you could solve the full multi-phase flow equations that I have scribbled above. And then all they really do is they add the ansatz that that the evolution of the volume fraction is a passive scalar, and so it's just given by this equation here. So basically, they just added this equation here as a compatibility condition to get the unknown volume fractions, and then essentially they did nothing with the rest of the terms. And so in principle, you could add all. I have not presented this with, say, the viscous terms here, but you could re-add those back in principle if you really wanted to. But in areas where you see Baer Nunziato being used, they tend to neglect heat conduction and viscosity anyway, so I did not sort of present them. Okay, and so Baer Nunziato, again, it assumes that all of the phases are fully compressible, and so that means that the density of each phase is a function of that phase's pressure and that phase's temperature. Okay, and so basically the Baer Nunziato, it relaxes the assumption of homogeneous flow, it relaxes the assumption of mechanical equilibrium, and it relaxes the assumption of thermal equilibrium. And some folks will add some relaxation terms here for drag to allow the two velocities to sort of approach one another, and it may or may not be a physical drag term, and they'll do the same thing with a heat transfer term too. Okay, and so oftentimes, and then for this we need to choose an interfacial velocity and an interfacial pressure. And for gas liquid or gas solid flows, it is very common to choose that the interfacial pressure is the gas phase pressure, and the interfacial velocity is the liquid velocity or the velocity of the condensed phase. Okay, and so those are choices. You do see other choices being used depending on application. And so the BN equations are used a lot in the explosives sort of community. And in fact, Baer and Nunziato, Baer, or basically Mel Baer, was at Sandia, and these were developed for high explosives. And so this is really meant for granular materials that are in a very, very compressible regime, where I mean where the solid itself is even the solid itself is very compressible. Okay, and like the 5 equation model, you need an equation of state for basically all of the phases. And one advantage of the Baer Nunziato model over the 5 equation model is that because each phase has its own pressure and its own temperature, that nasty pressure temperature equilibration step, you don't need to do that. Okay, and there are a lot of variants of this model, and there's a French mathematician called named Richard Zarl, and he's sort of one of the sort of modern BN gods, and so he does a lot of work on these type of equations. In my opinion, he does overuse them in applications where the inherent assumptions of the BN model are not appropriate. And I'll get into that when I discuss the next type of model. And also, as I said, the BN model can be they can be augmented with other effects. So, but if you work in high explosives, you will see the BN equations basically being used. Okay, and also a nice thing about the BN model is that if you apply homogeneous flow, pressure equilibrium, and thermal equilibrium, and then simplify them, you do wind up with the 5-equation model. Okay, so this is all I'm going to discuss for the BN, the sort of the Baer Nunziato model. I don't have, we don't use it in our group, so I don't have any fancy movies of the BN model, but a lot of the DOE codes have a sort of Baer Nunziato multi-phase option to soften. I think AL3D has one. I don't know how well it works, but I think AL3D has one. Maybe CTH, but
It
anyways.
doesn't work well.
Okay. Yeah, because there are there's a lot of math, there's a lot of trickery that you need to do to solve these equations, and so they are not easy to solve. Okay, so but if you work in explosives, like I said, you will encounter these. They're used quite a bit. But anyway, so now I'm going to move on to the next class of flows, and these are the ones that my group uses quite a bit. And here, our compatibility condition is derived assuming rigid particles. And so basically, what this means is that your equation of state is that the material density of the particles is constant. And so if the material density of the particles is constant, then if you work with conservation of mass down here, and you assume that the density is constant, you can basically factor out that constant density, and then I can divide both sides by that, and your conservation, and then your volume fraction equation basically becomes this, and then and that is also conservation of mass too. Okay, and so the volume fraction equation for this type of model, this looks like a very subtle difference. Basically, we're solving the sort of incompressible version here and an incompressible scalar advection equation there. But the difference in these two operators has an enormous impact on the flow dynamics. With the BN model, the particle volume fraction is a passive scalar. If you assume that it's not reacting, it's a passive scalar, and so a cluster of sort of a region of say alpha of the volume fraction equals to 1, it just moves around in space, basically passively along with VI. Okay, but in the rigid particle model, because this directly comes from conservation of mass, because we are assuming that the material density of the particles is constant, this equation itself is now is basically now compressible. And so basically models for rigid particles basically admit they admit shock waves, and so basically these shock waves can change the volume fraction. And let me look for a movie real quick that can show this very, very cleanly, that even though we're assuming rigid particles, the model itself is still compressible. Let's play. Excellent. This. Okay, so this is a movie I just stripped off of basically YouTube way back in the day, and this is called event-driven particle dynamics. And so what they do, so basically what they have here is they have a bed of particles, and they have an impactor, which is just a sort of densely clustered pack of particles. So they were studying like asteroid impact with this. But the point being, and the particles are all completely rigid, and there's no effects of the air, so you could assume this is in outer space where there is no gas. It's just pure particles, and so basically they just basically let this impact, and then you will see that after the impact, you will see a traveling shock wave propagating through this granular sort of layer here, and that shock wave is not changing the density of the particles themselves, it is impulsively changing the volume fraction of the particles. So you see the impactor going in, you see it impacting right here. And if I stop the movie, you see here, the impactor is sort of right here, and you see this sort of traveling front here, that is called a granular shock wave. And so, and this granular shock wave is impulsively changing the packing of the particles. And in fact, the volume fraction of the particles is acting like a compressible media. So even though the particles are not compressible themselves, the dynamics of a bed of particles is compressible. And at the surface here, you even see something that is analogous to a Prandtl-Meyer expansion fan, but instead of gas molecules that are expanding, it is particles. And so basically, even though the particles are completely rigid, we do see a lot of compressible flow, like basically of compressible flow like behavior basically for these particles. And now in the model for a completely rigid particle, you only get this sort of shock wave here if you solve a fully conservative style equation for the volume fraction. If you solve the sort of Baer-Nunziato version where it's a passive scalar, it is incapable of capturing the shock wave, because it's assuming that the volume fraction of the particles is incompressible, but the material density of the particles is compressible. And so, and their justification for making that assumption was not that they were in this this regime. The Baer-Nunziato model was developed for applications where you start with a sort of packed layer of particles to where they are already at the sort of maximum amount. They are already at their maximum packing. Is that you can't pour any more particles into basically into that mixture. And so if you're going to take that mixture, and then which then in terms of where you can't add any more particles because they're already touching one another, but yet then you take a 20 GPa shock, what's basically going to happen is that the particles themselves are compressible, and so basically the Baer-Nunziato is designed for that really highly packed, very high pressure sort of condition, and it's really specialized for that type of condition. Some folks try to use the sort of BN model for this type of flow, but it never works well because it's getting the physics right. And then now a very open thing and a very open sort of grand challenge of multiphase flow is, say if this impactor was moving at, I don't know, like 10 kilometers per second, you would have both these sort of compaction waves here. This is what this is called, or a granular shock, but you would also have the sort of particles being compressible. And so you would need a way to blend the Baer-Nunziato model with a basically with a rigid particle model, but that coupling does not exist. Right now, it is one or the other. And so basically you need to choose one. And if you have a type of model, which I'll go over next time for our current work on explosively dispersed particle combustion, is that even though for the beginning phases, a Baer Nunziato model would be more appropriate, but we are interested in the sort of dynamics of the particles themselves after that initial phase. But ideally, we would like a model that blends Baer Nunziato and the rigid particle model. But sadly, that does not exist. So let me go to the screen recording. So are there any questions on that?
It's basically if there's space existing between your particles, then you'd want to use the rigid particle method. And if there is no, if your particles are already touching, then you could use the Baer Nunziato.
Yep.
method.
Yep. Yeah. And just remember that basically Mel Baer developed that model with high explosives in mind, and the assumptions inherent to Baer Nunziato are really for those types of conditions. So the particles need to be they basically need to be touching, and they should be at extremely high pressure conditions like that of an explosive. Okay, yeah. In principle, you could use the Baer Nunziato model to do fluidized beds, but because the physics of the particle collisions and all that stuff are completely incorrect, it would not. I would suspect it would not work out very well. Okay, so and then just sort of carrying on. So that volume fraction equation, even though the difference looks subtle, it has drastic impacts on the physical interpretation of on the physical interpretation of the results of the model. And then after that, we basically add the standard conservation of species mass. That is essentially unchanged, except for now the context is it's not a nice fine interface in the computational cell. We now have a bunch of little particles. And so now our conceptual control volume, since we are in the particle phase, is a control volume that consists of basically drawing a control volume around all of the particles and basically averaging them together. And then basically if you do that, you basically wind up with the field equations for the particles. Okay, and then there is a conservation of momentum for the particles, and that is very similar to the conservation of momentum for any of the other models, except for we now, since we have actual particles here, we have to explicitly include drag models, and again, Bala's group is a world-renowned expert on picking those and developing them. And so I will refer you to his multi-phase flow class for how to model that. But there are any number of these, and basically some good and some bad. And one term here that we need to talk about is the so-called grad PS. That is an intergranular stress term. It's also called solids pressure, and it's called intergranular stress in gun ballistics. And in the fluidized bed community, it's called solids pressure. Okay, and then what this term accounts for, if you saw in that movie, there were all sorts of particles sort of banging into one another, right? Well, those particle collisions produce pressure-like forces. And those pressure-like forces are called solids pressure or intergranular stress. And so basically there are pressure-like effects from basically particles colliding with one another, are also frictional-like effects, as sort of if you are in a fluidized bed regime where you just have a sort of bed of, like sand in a glass or sand on a beach, you could imagine that there are layers of grain sliding over one another, and there are pressure-like effects from those grains sliding over one another. And we in our work we do model that term. Though the sort of models for this get rather complicated, and I'm not going to discuss them, but the sort of more recent ones are being developed from basically a sort of rigorous Boltzmann approach, where instead of tracking molecules, you basically track particles and apply the assumptions appropriate for particles. Okay, and then I will start with this equation here. Next time, this is a weird equation that you need to add for rigid particles that accounts for random translational kinetic energy. Okay, so that is it for today. Are there any questions? And so, yeah, we will finish up discussing the rigid particle models, and then I will do some show and tell of some recent work that we've been doing basically with the rigid particle model. Okay, are there any questions?